This video is about rule number 14, DeMorgan's laws. There's two parts to DeMorgan's laws, or two laws for logical equivalence. The first law tells us that the claim not P and Q is logically equivalent to the claim not P or not Q. The second law tells us that the claim not P or Q is logically equivalent to the claim not P and not Q. So in this video, we're going to talk about why that's the case. First, we're going to approach this conceptually. We're going to think of an example and talk about how this helps us understand the logical equivalence between this set of claims and the logical equivalence between this set of claims. Then we're going to talk about this formally. We're going to fill in the truth tables and prove that these two claims are logically equivalent to each other, and that these two claims are logically equivalent to each other. So first, we're going to do this conceptually. We're going to start with an example. We're going to fill in P and Q with some content to think about how this would work in a real-life situation. So let's say that P stands for Rebecca can pay her student loans. And let's say that Q stands for Rebecca can buy 60 pizzas. So this video is due on March 25th. And given how the past videos have gone, I would guess that about 75% of my students are watching this on March 25th. Well, March 25th is my last day in Italy. And that day, instead of doing work and really boring stuff, I'm going to Naples and I'm eating as much pizza as possible. But I have a budget because I have to pay my student loans. So I worked out the math, and my student loans payment each month is sadly roughly equivalent to what 60 pizzas in Naples would cost. Granted, pizzas are cheaper in Naples than they are here. Still a pretty depressing statistic. Okay, but those are our two examples that we have. So let's go ahead and fill this in to our claims here. So first we have not P and Q. So P and Q would be Rebecca can pay her student loans and Rebecca can pay 60 pizzas. Not P and Q would be it is not the case that Rebecca can pay her student loans and buy 60 pizzas. So looking at my bank account, that's correct. I cannot both pay my student loans and buy 60 pizzas. Okay, so not P and Q is Rebecca cannot pay her student loans and buy 60 pizzas. Not P or not Q would mean it is not the case that Rebecca can pay her student loans, or it is not the case that Rebecca can buy 60 pizzas. Or in a more natural way of saying this, we would say either Rebecca can't pay her student loans or she can't buy 60 pizzas. So we have, it's not the case that Rebecca can pay her student loans and buy 60 pizzas, because either Rebecca can't pay her student loans or she can't buy 60 pizzas. Hopefully that makes sense why those two things are logically equivalent. It's not the case that I can do both, meaning that either I can't do one or I can't do the other. Those two things are logically equivalent. Let's move on to the next one. So this says not P or Q is logically equivalent to not P and not Q. So we would say it is not the case that Rebecca can pay her student loans or buy 60 pizzas. That would mean that something like I spent way more money in Italy on Prosecco or something than I meant to, and now I don't have enough money to pay my student loans or to buy 60 pizzas. So we're saying it is not the case that Rebecca can pay her student loans or buy 60 pizzas. I'm filming this before I go to Europe, and this is totally hypothetical. I hope this is not the case. Saying hypothetically, I cannot pay my student loans or buy 60 pizzas. That's logically equivalent to saying I cannot pay my student loans and I cannot buy 60 pizzas. So if it's not the case that I could pay my student loans or buy 60 pizzas, that means that I can't pay my student loans and I can't buy 60 pizzas. Again, this is hopefully hypothetical, but hopefully we can see again how these two things are logically equivalent. If it's not the case that P or Q, that means that neither P or Q can be true. So if neither P or Q can be true, then we know that this claim, not P and not Q, is true. Okay, so we have an example. We've thought about this conceptually. Now let's fill in our truth tables. So for a truth table of two claims that are logically equivalent, so let's take two claims that are logically or truth functionally equivalent. What should we expect to see between those two truth tables? What is the relationship between those two truth tables? They should be identical. They're the same truth table. For two claims that are truth functionally equivalent, they will have identical truth tables. So what we're saying is that we expect to see that the truth table for not P and Q will be identical to the truth table for not P or not Q. Before we start, let's talk about what I've written down here. So under each claim, I have written primary LO. That stands for primary logical operator. So when we're comparing the two truth tables to see if they're identical, we need to compare the truth table under the primary logical operator, or the logical operator that's doing the most work, the one that's doing the heavy lifting here. So in not P and Q, we have two logical operators. We have negation and we have conjunction. Which of these two, negation and conjunction, is going to be our primary logical operator, do you think? Which one is doing the most work? Negation is our primary logical operator. Oh, I did not erase this from the last time I tried to film this. So you already had that there. Our primary operator was negation. Great. So we know that it's negation. This one's a little bit easier because it's just outside of the parentheses. It's just like math. You do whatever is in the parentheses, you do that first, and then you move outside of the parentheses. And your primary logical operator is going to be the thing that you do last, the thing that you put on last, the thing that you're solving for last. Okay, so our primary logical operator here is negation. Let's go ahead and fill in the truth table under our secondary logical operator, which is conjunction. So we know that conjunction is only true if both of the conjuncts are true. So conjunction claims are only going to be true in this first row where both of the conjuncts are true. Okay, so now let's move over to our primary logical operator. I'm going to write this truth table in green to separate it. What does the truth table under our primary logical operator look like? Okay, so we're negating this whole claim, P and Q. So what we're going to be negating is this column here under the whole conjunction claim. So when we're doing negation, we just flip the truth values. So our first row, we're going to have F, and then in all the other rows, we have T. So not P and Q is true in every situation in which P and Q is false. Okay, so we have F, T, T, T. Let's move on to our next one. I've already filled in the truth values for the negated variables here in red. So what does our truth table look like here under our primary logical operator, which in this case is disjunction? So for disjunction, we know that it's true as long as at least one of its disjuncts is true. And the one row in which both of its disjuncts is false is row 1. Row 1 is the row in which not P and not Q is false. So we know that the whole disjunction not P and not Q is false in row 1, and it's true in every other row. Okay, so we're comparing the column under our primary logical operators. Are these two claims logically equivalent according to their truth tables? Yeah, their truth tables are identical. Awesome. Okay, let's move on to the next set. So here, in this claim, what is our primary logical operator, negation or disjunction? Our primary logical operator here is again negation because it's outside of the parentheses. What's our primary logical operator in this claim, not P and not Q? It's conjunction. So conjunction is the one that's doing the most work. Negation is really only going to be your primary logical operator if it's the only logical operator or if it's outside parentheses. Okay, so here we have P or Q. So let's go ahead and fill in this truth table. In which rows am I going to have a T for true here? Rows 1, 2, and 3. This is a disjunction. All right. And what is my truth table going to look like under my primary logical operator? It's going to be flipped. So we're going to have false, 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 true. It's the opposite of the truth value of this whole phrase P or Q. Okay, so what about in our next claim? So not P and not Q. What is my truth table going to look like here? it's going to be, again, we're looking at the conjunction of not P and not Q. So it's false in every row except for the last one, in which both not P and not Q are true. So again, here we have the truth table for our one primary logical operator here. Here's our truth table for our one primary logical operator in our second claim. Are these two claims logically equivalent? Yes, they have identical truth tables. Okay, so we talked about this conceptually, how these are logically equivalent, and we've also done the truth tables to prove that they are logically equivalent, that they have the same truth conditions, or that they have identical truth tables. Okay, so that's it for DeMorgan's laws. In the next video, we're going to do some practice with some arguments using full rules of deduction. So let me know if you have any questions about the rules of deduction that we've covered in these videos or ones that we didn't cover in these videos.